So welcome to this channel Chemistry Made Easy by Dr. Ashok Mulik. We were discussing the molecular orbital theory, and in which today we are going to see homo-nuclear diatomic molecules. Here we are discussing the molecular structure, and before that we have seen various theories like Levy's theory. So Levy's theory tells us very simple type of structure using the Levy's dot formula. We have seen already that Levy's dot structures, and these Levy's dot structures are useful to predict about the structure of molecules in case of nitrogen, oxygen and fluorine. But in case of the molecules like lithium, beryllium, boron and carbon, this Levy's dot structure cannot work well because these molecules have insufficient or electron deficient octets. The octets are not completed, and therefore the electron dot structure is not sufficient to explain about the structure of molecule. Further, the structure, the molecules which are formed as a result of linear combination of atomic orbitals, we have to follow the above principle and exclusion principle, Pauli's exclusion principle, Ohm's rule of maximum multiplicity, etc., in order to fill up the molecular orbitals. Similarly to that, we have used for atomic orbitals. So we are going to fill the lowest energy molecular orbital first, and each orbital may contain maximum of 2 electrons. So we have to follow here all these rules. Then we have to see that bond order is another concept. So bond order is given by 1/2 of the number of electrons in bonding MO, bonding molecular orbital, minus number of electrons in anti-bonding MO. So this will give us the bond order, means multiplicity of the bond, means the number of bonds which are binding or holding the 2 atoms together. For example, if we consider nitrogen molecule, that is N2, there are 3 bonds, out of which one is sigma and 2 are pi bonds, which hold the 2 nitrogen atoms together. Then we must know that there are different terms used in discussing these molecular orbitals. So the first term is Gereid, G for Gereid, and another is U for ungereid. So G and U are the terms. So the G indicates that these are the orbitals which are showing the symmetry with respect to inversion. So these are symmetric to the inversion, means there is no orbitals, the change in sign of wave function is not observed, means they are symmetric to inversion, means there is, even after rotation about the internuclear axis, there is no change in sign of wave function. In case of ungraded, they are anti-symmetric to inversion, means after rotating these orbitals about the internuclear axis, you will find that they are showing the rotation, change in the sign of wave function. So in this way, so after inversion, there is change in sign of wave function. So they are called anti-symmetry. Then you will see how is the molecular orbital diagram constructed. So first of all we will see this is energy axis, and along this we are arranging the atomic orbitals as well as molecular orbitals. So first of all we will place here the atomic orbitals of say A. We are showing here in this direction the atomic orbitals of another A, because we are considering homo-nuclear diatomic molecules. Homo-nuclear diatomic molecules. If it is heteronuclear diatomic molecule, we can take here B. Instead of A, we will take another symbol, that is B. And now there is center of this diagram indicating molecular orbitals of A2, that is homo-nuclear diatomic molecule. Now here we have to represent that this is 1s and this is 1s. So both are the atomic orbitals of the same element. So their energy levels are also same. 1s is also placed at the same energy level. So linear combination of this will produce the two molecular orbitals. And here this one is sigma and this is sigma g and this is sigma u star. Then we will have another 2f orbital which is higher energy than 1s. So we will take here this 2s. This is 2s of another atom. So after linear combination they will produce one bonding. So this is bonding molecular orbital called sigma g. So this is sigma g bonding and this is sigma star u, that is anti-bonding molecular orbital. And after this we will have the 2p orbitals. 2p orbitals. So there are such three atomic orbitals in 2p level. So as a result of this there is formation after linear combination. There is formation of a molecular orbital called sigma g. Then there is formation of pi molecular orbitals. Like this. So we will show here pi u and both are pi u. So we will see here that it is pi u1, pi u2 we can represent. Then after linear combination they will show two antibonding pi nature molecular orbitals. So these are called pi g star and this is also pi g star molecular orbitals. After linear combination between atomic orbitals of sigma type, that is pz, will give us sigma star u. Sigma star u is obtained. Now if we see what are the atomic orbitals involved in this type of bond formation. So you can have say this type of, say this 1s. So this is 1s, this is 1s. So they will produce the molecular orbital of these two nature, that is, so this is the nucleus. Then we will have this sigma g orbital and there is sigma u orbitals, sigma star u. So we will have this type of sigma g and sigma u. Here is change. So So these are the sigma G and sigma U. So you will find here sigma G and sigma star U. Then similarly is the case here. So there is 2s orbital. So you will have 2s, and there is formation of the bonding molecular orbital like this. So there is formation of bonding molecular orbital that is called sigma G, and these are antibonding molecular orbitals called sigma star U. Then we will have this sigma G obtained from the pz orbitals. So we will have sigma G obtained from pz orbitals. So we are having pz like this. So we are having pz like this, or we can represent these orbitals in different way like this also. So these are the two lobes. So out of which one is having plus sign, one is having minus sign. So they will undergo linear combination to form these molecular orbitals like this. So the pz orbitals, two pz orbitals are there. So we have shown only one here. So plus we can say here like this. So we will get this sigma G orbital. So we will show here in front of this. There is like this, and we will have the antibonding sigma orbitals. We will show it here. This is antibonding molecular orbitals. So we can show these molecular orbitals in this way, or in other words, we can also show these orbitals. Here you will find that like this. So the two lobes of same sign, identical sign, will merge with each other, and the other lobes will remain like this, unchanged, like this. So this is the sigma G. Now you will find here the antibonding orbitals like this. See, this is one lobe, this is another lobe like this. So we can have the signs of wave functions like this in these molecular orbitals. Now we will have the p orbitals of fine nature. So these are, we will show here pz orbitals. Now we will show here the p1 and px orbitals. So these are lying in the direction of x and y axis. So as a result of this, they will give us the different shape. So shape of these resulting molecular orbital will be like this. Say this is for one pi bonding molecular orbital. We will show here it is. So for one molecular orbital of pi bond in nature, you will have the two loops, means one of them will have so py or px px. We can consider any of them. So structure is same. So they will show the overlap like this. So there are two electron clouds. These two lobes of this orbital of pi u nature. Say one has plus plus sign of wave function, this has minus minus sign of wave function. Similar is the case of another pi. Here in case of antibonding molecular orbitals, we will have the bonding means antibonding molecular orbitals of this way. So we can have the lobes like this. We can show the lobes in this way also. Now we can have the signs of wave functions. Say this has minus 1 up, minus sign of wave function, this has plus sign of wave function. This has minus sign of wave function, this has plus sign of wave function. So they are repelling each other. So we have shown only one type of, say using here, we can consider here py. So we will see here the linear combination between py, or we can have px, any type. So we have taken here only one of them. Example means this is only one pi orbital having its electron cloud above the internuclear axis and below the internuclear axis. And in this antibody pi nature of orbital, the electron clouds are repelled and they are moving away from the nuclei to nuclei. So the electron density is here not 0, and therefore this is called a nodal plane. So there is also one more node like this. So here you will have, say there is such nodal plane, node. So there is also node like this. So these are nodal planes. So here you will also find that the node is like this in vertical direction. There is node in this way. So there is no node. Here also you will find the node, is that region around this atom or nucleus having electron density 0. So this is about the various atomic orbitals and molecular orbitals involved in the formation of the molecular orbitals which are required for representation of the homo-nuclear diatomic structures and molecular orbitals for first 10 elements. We are considering only the energy level diagram for first 10 elements. This is general structure of energy level diagram or molecular orbital diagram. But actual structure may vary depending upon the actual molecule. So that will be discussed when we will see that particular molecule. So we will stop our discussion here and we will see the next point in the next lecture. So till then, goodbye. See you next time. Please subscribe to this channel, share this channel and press bell icon and like button. So thank you very much.